Welcome to the Crazy Hat Chemist. So another video here on Intramolecular Forces. Bam! So today we're talking about intramolecular forces between ion and ions. So I know this is a whole unit on intermolecular forces, but we also need to compare those to intramolecular forces. So intramolecular forces between ion-ion interactions. So the strongest intermolecular forces are in ionic compounds. Those are salts. They're solids at room temperature, okay? They're crystalline structure. Sodium chloride, table salt, is the perfect example of this. Okay? Salts are composed of a positive cation and a negative anion. Okay? And they're held together electrostatically. Okay, here's a model of this right here, and I have this here made just for this video here. So I got sodium chloride. There's the sodium ions are the blue ones, and the chloride ions are the green ones. Okay, the attractive force can be measured using Coulomb's law. Okay, and this is Coulomb's law. Coulomb's law is the following. The force is the electrostatic force between the two different ion charges. This is the Coulomb's law constant, and this is the point charge number 1, point charge number 2, i.e. the cation and the anion respectively in this case. And this is the distance between the charged centers. Okay, so an application of Coulomb's law is with a salt, and we can figure out which salt has the highest melting point, sodium chloride or magnesium oxide, and then we can figure out why. So here is Coulomb's law. I've plugged in a couple of values here for you. One is the periodic trend charge for sodium, and that is a +1. That's why there's a 1 for the sodium. And then the periodic trend charge for chlorine, the chloride ion, and that's also a 1. So my numerator term here is a 1 times a 1. Okay? Now, let's take a look at magnesium oxide. So magnesium is in group 2, so its periodic trend charge is a 2+, and oxide is a periodic trend charge of a -2. So therefore my numerator term here is 2 times 2, that's a 4. Okay, now the other thing we need to look at is the distance between the sodium and chloride, and then compare that to the distance between the magnesium and the oxygen. Now we are looking at our periodic trends. As you go down a group, they get larger. As you go to the left within a period, they get larger. So if you compare the relative sizes of the sodium and the magnesium, and then compare the relative sizes between the chlorine and the oxygen, our answer will be arrived here. We don't actually have to get the physical numbers. So magnesium is smaller than sodium. Okay? And furthermore, oxygen is smaller than chlorine. Therefore, the distance is smallest between the magnesium and the oxygen, and that is in the denominator term. So that denominator term is smallest for the magnesium oxide, and yet its numerator term is larger. Okay, the constant, the Coulomb's law constant, is the same for both, so we can effectively ignore that. So if the numerator term is larger and the denominator term is smaller, the force is going to be greater. Okay, so that's what this is saying right here. Magnesium oxide has a higher melting point. It's 2800 degrees Celsius for magnesium oxide in comparison to sodium chloride, which has a melting point of 800 degrees Celsius. A significant difference, and that significant difference is seen in Coulomb's law. That is, the numerator term, due to the charges of the magnesium and the oxygen, are much greater, so that numerator term is larger. And furthermore, that denominator term is smaller because magnesium ion is smaller and oxide ion is smaller than sodium ion and chloride ion respectively. This makes the force greater and therefore the corresponding melting point higher. Okay, and hopefully you remember this here at the top of the screen. Delta H, that is the change in enthalpy, is equal to the sum of the bonds broken minus the sum of the bonds formed. We have talked about this before here, and that is your best friend. That's the B and the F, best friend. So a prior energy calculation of intramolecular forces in covalent and polar covalent bonds with this energy calculation, and we have done that before, and you can do that same thing, and it does correspond to the values that you get for Coulomb's law. So that's another verification of Coulomb's law. Okay, I am the Crazy Hat Chemist, and I got a crazy hat here for you today, and here we go. What am I? I am not an onion, I'm a garlic, and that's from my heritage. Give me a thumbs up if you like that video, subscribe to my YouTube channel, and look for more on intermolecular forces, and I'll see you next time. Bye for now.